Hey everyone, it's great to have you with me, especially so late in the afternoon. Looks like we got a couple of minutes head start, so I'll get straight into it. So the background for this comes from the chaos that's happened over the past several months as we, like just about everyone, try to figure out ChatGPT, and I think probably in part driven by a lot of fear, how do we make this thing work? Because if we don't get this right, we're going to have some problems down the track. And so the most obvious place for us to start out was to look at how we could use it as a power tool, and I think that's probably fairly well understood. Certainly as a developer, there are a lot of ways that it helps to accelerate you. If you're like me, a lot of the time it's 50-50 whether I'm going to use Google or ChatGPT to get some answers. And especially, over time, as you start to understand its failure modes, what a hallucination looks like, and how to kind of identify that, it really has just become another tool in the tool belt. But one thing that we really wanted to look at was how we could augment user experience in our platform. And for the past decade, I've kind of been keeping an eye on machine learning, but just never really felt it was at a point where we could reliably get something done that wasn't ever going to create a frustrating user experience. And particularly kind of confirming that fear is what I feel really happened with chatbots going back a few years, where you're talking to a bot, you're talking to a bot, it doesn't know the answer to your question, and you still got to go through it anyway before you can get to a real human. And so with some reserve, we sort of felt that the threshold had been met, that this tech is sufficiently sophisticated that we could deeply embed it within our platform, and this is the result of that exercise. I would say where we're at today is still technically experimental. We're not shipping this in the wild, but hopefully this helps some of you if you're also at this point where you're trying to evaluate how to make ChatGPT work in your own platform. So to begin with, how do we start? One easy way that we found to get in is actually to sign up to OpenAI services via Azure. Actually, the waitlist on that wasn't even as long, and then when we needed to request access to the GPT-4 model, for example, and then the 32K model, again, that got done within about a week. One useful upside to this approach as well is that you can make it available to your team very easily. So if you go to OpenAI, you're going to create a $10, $15 subscription per person, and you want to do per person because the history is shared, so it needs to be isolated. Whereas if you do this through OpenAI under Azure, you can build a little app and then actually give access to your whole team. So we started with OpenAI services. We're using ChatGPT 3.5 Turbo. It's really not that fast. But we found 4 incredibly frustrating. Months later, the rate limiting is still very extreme. And I'm a big believer in very fast, iterative cycles when you're building. If you have to wait 30 seconds to get a response, that's like really slow when you're trying to iterate on a prompt. Another really important thing for us was to get a high level of determinism, in fact, a perfect determinism out of the output. In other words, if I give it this prompt, I need to get the same exact answer back every time. And when you can do that, that means that you can actually unit test this stuff, which means if you change your strategy around prompts or you tweak some of the dials and levers, you can rerun your batch of unit tests and make sure that there's no regression on anything that you've previously built. And the way to do that is through a lever, a parameter called temperature, which is effectively a measure of creativity. So 1 is max. You want to use that if you want pros and so on. But I think for our purposes, anything technical where it's got to be exactly right or as close to that as possible, you want a low temp. There's also a great toolbox that Microsoft provide where you can take a look at the models that you've deployed and run tests against them. So this is what it looks like, Azure AI Studio. And in here you can see the deployments that I have available. And we've got 4 deployments sitting in here. And apparently a constrained internet connection. Okay, so as I mentioned, we're working with ChatGPT 3.5 Turbo. Then we've got the 8K and the 32K model. That K, if you're not aware of this, is the number of tokens that it can take on its input. So if you want to work with very large amount of documents as input, or you want it to produce large documents, you want to use the 32K model. It's double the price, so it gets expensive fast. But 32K is a lot of tokens. A token is approximately a word of 4 characters. If it's longer than that, it'll become multiple tokens. And then finally, we've also got a much earlier model called Adder, and we use this to do a vector search, which I'll get to a little bit later. It's got quite a nice playground over here. There you can see that temperature model. You can basically just type some prompts and get some answers. So, just as a quick way to iterate, that's pretty useful. So there are 4 areas that we looked at incorporating into the platform. We are expecting to add others, but these are the ones that we've had some success with so far. So our platform lets companies connect different apps and services together. And so as soon as you're moving data from one product to another, you necessarily have 2 different schemas, a source schema and a target schema. And so a critical stage in most integrations is that you need to map those fields from source to target. Sometimes they have the exact same field names. Mostly they don't. And sometimes the mapping is heavily dependent on the context. So if I'm looking at 2 different sales orders, yes, I might need to map quantity to QTY, but sometimes the interpretation of that depends on the surrounding field. So something that a human doesn't find that hard to do, and it happens to be something that ChatGPT is quite well suited to as well. So we call that semantic field mapping. Then as an extension of that, once you've mapped the fields, you also need to run some expressions against them. So you might need to run a calculation, you might need to truncate a field that's going to be too long for the destination. And so we wanted to come up with a way that someone could type some text and then have it produce an expression, basically a code fragment that would perform that translation. Then we wanted to look at how we could take the design of a workflow and actually have ChatGPT document it for us. And then finally, a way to get contextual help that hopefully goes beyond a traditional chatbot. So the way that we implemented this out is we created an iHelp interface inside the platform, and then we created various implementations against that. Basically, what you're seeing, that first parameter is the key, so that signals the type of action that we're going to be taking against them, and those 4 areas are the 4 areas that I had described in the previous section. So we feed it a key, a payload that is pertinent to that key, and we get a result back. And that's published as an API that our console, which is a SPA, can call directly. So all of the heavy lifting gets done on the back end. So let's have a look at this. I'm going to start out looking at the quick map feature, which is our visual data mapper. So that's the stage that I showed you earlier where we map from a source to a target schema, and we wanted to be able to infer mappings, basically just to kind of give you a leg up on getting started there. So in the platform, I'm going to go create a new workflow. And what we'll do is we'll query a SQL database. I have one running on my local machine, so this is my SQL query here. I'm going to plug in some query text. So I have a connection that I've created, and I've got a table in here called contacts. So we'll go and run that. And what this is doing is it's giving me an activity log showing the stages that just ran, and I can drill into the result, and that's a tabular view of those 10 or so contacts that came back. So I've queried my data source. And then we want to build a pipeline, for example, that's going to ingest data into Salesforce. So I can add the Salesforce connector onto the canvas. And then importantly, I need to understand how Salesforce needs me to send data to it. So I can go into the choose sample area, and that will use the metadata that the Salesforce API makes available to present a list of all of the interactions that are available there. So I'm going to choose the create contact schema. And in a minute or two, that should load up the schema. So here we can see an example payload. So Salesforce needs us to present contact information in that form. So that's all by way of introduction. Now what I want to do is put our visual data mapper in the middle. And that's what this looks like here. And it needs to see, as I mentioned, our source and target schemas. So I'm going to take the output from the SQL stage, plug it into the source, take the output from QuickMap, plug that into the source for the Salesforce stage. And now QuickMap has a view of both source and target schemas. And when I drill into that, it's able to infer a schema for me now. And 2 tree views emerge. Left-hand side is the source schema that it's inferred from the data that I just queried. And then in the middle is the schema from Salesforce. And what we're going to do now is get it to map these fields as far as it's able to. And I do that by clicking that auto map button. So it's busy with a ChatGPT invoke right now. And you can see it's created some mappings for us. So none of this is based on rules. This is purely by feeding a prompt into GPT, and it came back and told us what mappings we should be using there. And over on the right-hand side, you can see what a preview of that data looks like. So it's correctly figured out first name, last name. It's mapped some address information, phone, email address, and it's done that. In this case, it's done it primarily by matching fields that are very similar, but automatically nonetheless. Let me show you one that's a little bit more involved. So here we have same thing set up, so quick map. This time we're looking at 2 different schemas. One is a simplified sales order, and the other one is a schema for a sales order in an ERP called Syspro. So we're going to run that mapping again. And this one requires it to maybe flex a little bit more. And you can see here it's produced some pretty meaningful mapping. So on the right-hand side, it's showing me an order header. Now you'll notice that we had a bunch of rows as input, and so below the order header, it's putting the next order header. That's actually a mistake. But look at the mistake it's made. It's the same as what a human would have probably done. On the left-hand side is a single order. On the right-hand side is order header. It's a reasonable inference. But actually the way this particular schema is designed, I need to map it onto orders instead. So in a sense, it's wrong, but it's actually doing exactly what a human would have done. So if I fix that mapping up, it now shows me the order header over there. And if we go down to the detail section, it didn't map the container here. So I've got line to stock line, for example, is how I need that to be mapped. And if I fix that, I can see it's mapped these correctly. Here you can get a sense of what it's doing. So total cost price, it decided to map that to price, quantity, order quantity, and so on. Inventory code equivalent to stock code. So pretty useful technique. Let me show you what's going on under the hood here. So a little small on the screen, but these are the 4 implementations that we've got. So we're going to look at the quick map auto map, and we're just going to put a breakpoint onto where it's going to generate those mappings by invoking GPT. We'll just rerun that. And so we have 2 different classes of prompts here. We've got a system prompt and a user prompt. So in GPT, the system prompt is kind of what guides it, and the user prompt is what a user is meant to be putting in. So the OpenAI system prompt says, you are ChatGPT, your knowledge cutoff is this date, and so on. And when you get API access, you can override that system prompt. And it's supposed to listen more closely to the system prompt. That kind of keeps it within the rails, or the guards that you want to set for it. So what we've done on the system prompt is given it a statement around you're going to be presented 2 schemas, and present back the answers in this form. So show me the source path in XPath form, and then show me the destination path that you want to map to. What we found is really helpful is if you actually give it examples of what you're going to do as well. So then we show it, here's a source schema, and it's capable of understanding that because of this indent, that means customer belongs as in like a hierarchical nesting under customers. Same thing goes for target schema. And then at the end of it, we said, here's an example mapping. Here's what I'm expecting you to give me back. Show me that source field maps to that source field. And notice, customer and debtor are treated as synonyms there. So that's the example we gave it. And then in the actual prompt that we're going to invoke it with, basically just a string template, here's your source schema, here's your target schema, and those labels correlate to the labels that we sent it into the system prompt. So if we have a look at how that resolved, here's what we're sending in. Here's your source schema, and there's your target schema. And on the reverse side of that, it's going to get a response back. We'll convert that prompt to the mapping format that we use within Flowgear. But I want to show you how to deal with failure here, because this can happen as well. And I think this has been a key insight for us, is you've got to be able to handle a degraded response. So one useful thing is that I've seen a lot of people trying to get it to emit JSON. And then, in some cases, it just won't give you JSON back. It'll just truncate the doc, or it'll be syntactically invalid. It's actually easier not to ask for a structured document. Ask for something that's closer to text, more like a YAML, that you can do a soft parse on, and then skip over anything that's unusable, but retain anything that's usable. So I want to show you an example of this one. This one's problematic. It has a ton of mappings that don't map properly. So we're going to just let that run. So this is the logging showing up here. I think this one takes a bit longer. It's a fairly big schema. It's that moment whether you wonder whether the internet connection's still going. There we go. All right, so we're just dumping it in the logs here. You can see the summary. So that took 30 seconds, and that, by the way, that's ChatGPT 3.5. This is why it's important to try and get as much speed as you can out of this. It's showing us some information about the number of prompts used, but have a look here. It gave us 43 mappings back, but actually 26 of them were syntactically invalid. Now, because each of those mappings is just broken onto a new line, it's very easy for us to parse that and then degrade the response gracefully. So if we don't encounter a mapping that is a viable field, then we just skip that one. And despite all of those, there's still a significant number of mappings that are valid, as you can see over here. So a key thing for us was just understanding that, like partial degradation, is actually really useful if you can get some benefit out of a prompt that's failed to a certain extent. So essentially what's happening here is you're getting some time saving. Also for people who are newer to the platform, gives them a much better sense of how to consume the quick map tool. So you're getting a baseline view that you can iterate on from there. The next thing is once you've mapped fields, normally you need to add some kind of expression to trim those fields or perform some kind of calculation on them. There you can see an example of trimming a name, maybe to 5 characters, for example. So here, a lot of the time, if you're new to the platform, you don't know how to write those. It's not a language you have worked with before. Now, actually, the language that we use is very similar to Excel. So what was convenient for us here is ChatGPT already understands Excel formulas. So we can kind of nudge it in the direction of, hey, you need to give us an Excel formula that is representative of this text statement. And we found that in most cases, it actually did a great job of it. And in places that it didn't, it was because the way that we've built these functions are different to the way Excel works. So we made changes to our mapper instead so that it falls more in line with the way Excel works, and that gets us a higher level of accuracy. So let me show you an example of that. Let's say we just needed to combine these fields together. So we got a first name and a last name. Let's just go and combine both of those onto one field. My map is going to error now because it doesn't know how to combine those fields. I haven't given it an expression telling it how to do that. So what I can do here now is go to this describe a function option, and over here we can give it a prompt. Notice I'm just saying combine names. I'm not telling it which names to combine, but it is going to be, as part of its prompt, it is fed the names from the source schema that have been plugged in, and it built this concat function to be able to do that for us. So that built a syntactically valid expression, and if I scroll up here, I can see that it combined those names. And notice also that it decided on the order in which those names should be combined. It put first name before last name. None of that was done by me explicitly. So a really nice way to get something working quickly. Let's look at one more example. Let's say we wanted to produce a username. So say, take first letter of first name, followed by, I'm going to say surname, which is not what the field is. It's called last name. And then say no spaces, for example. So you can see, again, it gave me a left function for that, and there's my sort of pseudo username that is produced there. So we found this pretty useful. I'll show you what the prompts look like for this. So we'll just trigger this again. All right, so this time around, here's our system prompt. We're telling it that it's going to be given an expression, maybe a little small on screen here, but this is telling it the list of fields that have been mapped into the target field that we're trying to build the expression for. And then what we've done here is dumped out a listing of all of the functions that have been defined within QuickMap. So it's kind of operating like a co-pilot for us, right? So that's the function name and then the list of params, and it's VBNet syntax. So this is actually a comment that explains how to use it. And in most of these cases, we explain how each of these parameters interact with each other. So GPT is actually able to use that as part of its prompt to figure out how to get us a working expression back. So another example is a way to describe a workflow. I think if you're like me as a developer, you hate writing documentation. You hopefully started your project with a spec, and by the time you're done, it's a bit like a tire swing cartoon, and what you've ended up building is very different to where you started, and then you have the joyful task of building documentation. So we wanted to look at a way that you could leverage this tool to be able to get you at least a baseline level of documentation. I'll show you what that looks like. So we're going to go back to the workflow design, and we can just click this document button over here, very straightforward. It's just going to try and infer what the purpose of this workflow is. And here you can see it coming back. So it says it's querying a SQL database. It maps it to a Salesforce object. It triggers from the SQL query. The results are mapped using QuickMap. Finally, we're creating a new record in the Salesforce node and so on. So pretty useful. But what's also super interesting about this is we found with customers when they have a lot of workflows in play, it's like having a large code base. If you're like me, when I'm trying to figure out where to go, I remember a fragment of an identifier or a constant or a class name. So I'm constantly searching the code base, right? And so one of the difficult things with this is how do you search a workflow that's been designed visually? If you actually have a description of the workflow that's stored in the platform, and then you can search in that, it makes it much easier to figure out where certain things are taking place, especially when there are hundreds of workflows. So how do we get it to describe what's happening on screen here? Again, I'll put a breakpoint on this. So this is the workflow describe function. Here we go. Yeah. Okay, so what we needed to do here is find a way to strip out the workflow so it was much simpler. So this is the underlying JSON document that describes workflows. There's a lot of information in here that isn't relevant to being able to write a spec. For example, GUIDs, governance stuff, position of things on the screen, large payloads, etc. Plus the fact that it's JSON, each of these curly braces, commas, quotes, colons count as a token. So we wanted to reduce the token usage on this as well. So we did this in a few steps, but essentially what works really well is converting the JSON out to YAML, which obviously has a lot less syntactic baggage, and then stripping out things that are not relevant for purposes of building a description as well. So we actually end up with a user prompt that looks something like this. So you can see it's basically YAML, and then we've just stripped out the stuff that doesn't matter to create that description. This has been very effective for us. So I would say that reduces the token count probably by about 75% as compared with the raw JSON input. You know, you can put it through its paces. It understands stuff it's never seen before, and then if it makes mistakes on certain areas, you can just correct your system prompt to guard it against those specific classes of mistakes. We found that very effective. So the last thing is looking at how we can do a help system. And there were kind of a few ideas that we had around this. One was that we have help articles that users can already search, but we wanted to provide much more contextful help to them. And then the second is that we had a reasonably large corpus of support interactions, especially through our chat. And we wanted to see if there was a way that we could generalize those things so that it could be useful for future. This is kind of like the lazy way of doing documentation, right? Like take all of your support history, generalize it, and then feed that into something that can do something useful with it instead of improving your help articles. Like, of course, eventually you want to improve your help articles, but this allows you to do it at a rate that's hard to match. So we had some great success with this. We took chats, I think we had a few thousand of them. We took out sensitive bits of data and rendered them out to text. So here you can see kind of the gray text is a user asking a question, the white text is our team responding. And in this particular case, the question is, why can't I publish something? And the answer is that you need to have a certain level of access onto the accounts area in the platform. So that's what's going on in the text of this thing. And feeding that into ChatGPT, we gave a prompt that says, generalize this into troubleshooting advice. Don't emit anything that's specific to this particular scenario. Don't emit endpoints, URLs, email addresses, phone numbers, etc. But write a one-line statement on what this solves, and then the kind of response in a few paragraphs on what that help looks like. And this is an example of the result that came back. I'll be honest, we have cherry-picked some of these. I would say your hit rate on this is probably 20-25%, so 75% of it's very questionable, but that 25% is pretty golden. And what's useful here is you could take this as, say, a markdown file. You could push this to a branch in your code repo, and then you can have some poor soul can help with that PR, right, and figure out whether you want that in your master branch. So some kind of review is necessary, but it's got to be like at least 100 times faster than writing the same content into your help article. So it's a really nice accelerator. Now, we had some trouble here, because how do you feed it this knowledge? Now, as it happens, our help system is public to the internet, and we do think that a lot of that content was in the training corpus, because it's able to say some things that are super specific, but we have no very precise control over it. So we actually need it to feed it very specific information that belongs to us, our support information, our help article information. How do we do that? Because it's far too much to fit into a prompt. And even if we could, it would be prohibitively expensive. So you basically got four options. You can do a model retrain if you have hundreds of millions of dollars, or you can do a fine tune on top of the model. And so what we're seeing a lot of vendors do now, Microsoft and Google are doing this. You have a base LLM model, and then you can fine tune it on your corpus. That's actually pretty hard to get right, because if you mess it wrong, you'll actually break the underlying LLM implementation. So we felt that wasn't an easy way out. The other one that's coming is plugins. So plugins can be used, you can have private or public plugins. So for example, Bard launched with a web browser plugin. So in theory, it can at its discretion decide to do a search and then incorporate that content into its prompt. So that's how it pipelines it. But the way that we found works incredibly well is a vector search. So this is quite a sophisticated search that I'll explain how that works. And then we take the most closest matching help articles and troubleshooting tips, and we feed those into the user prompt on GPT, and then get it to formulate that into a response for us. So this is what the pipeline looks. You've got to do two things. From a setup perspective, you've got to feed your help articles and ideally also your troubleshooting information in some form into and calculate embedding vectors. So what's happening there is you're getting the text of each of these documents. You're feeding it into that other machine model that I told you about earlier, that adder 002. And what that does is it comes back with a highly dimensional vector. It's basically an array of 1,500 floating point numbers that encompass the semantic meaning of that article. And then you store those, and our corpus was small enough that it was a few megs, so we store that with the raw text in a database. And then when a user asks a question, we take their search term, we run that through the same language model to get an embedding vector back. And then we run a function called a cosine similarity that evaluates across each dimension how closely that vector or that element matches another element. And basically, the higher the score, the more similar it is, the lower the score, the less similar. So you run that ranking against all of the articles in the corpus, you sort by score descending, and then you take the top, say, 3, and you put those into your prompt at the top, like your user prompt, and then you say to ChatGPT, given these articles, answer this question. And it works remarkably well. So I'll show you what that looks like. So we'll go and just have a look at the search function here. So here I can open the troubleshooting section. And I'm going to start with something easy. I wanted to explain a particular function that we have in QuickMap. That's the tool that you saw a little earlier. So there's a function called left of. So we'll just say explain left of in QuickMap. Let's try and just run through some of this so I can show you what that looks like. Okay. Right, so here what we've done is we've taken a search term, explain left of in QuickMap, and we've generated an embedding. And this is what it looks like. So it's literally an array of 1,500 floating point numbers, and that encompasses the semantic meaning of that search term, and that's where that cosine similarity algorithm comes in. So the next thing we're going to do is we got 270 documents in the corpus. We're going to iterate through all of those and then calculate that similarity. So we'll go into the first one. This is basically what it does. We work along each vector, and we want the dot product as the result of that. So we're going to come out of here. I'll just show you what these scores look like on the back of it. So we now have a similarity score. I'm getting a 0.6 there, so that's the degree of similarity that it thinks this current candidate document has with the search term that I created. And we iterate over all of our documents until we've got a top 3 set of results. So we'll let that process finish. And then we're going to take the top 3 documents descending. That's what this comma 3 is doing, and we're converting it out to a list. And then we're going to inject that into the system prompt. So here's the prompt. So here the prompt is use the help articles below to respond to the user's question, and then we're just literally dumping all of the documentation right into there. So three help articles. I think they're separated by some line breaks, and then the user prompt is the specific question that the user asked. And here's how that surfaces. So we're invoking ChatGPT. So two stages. One is we needed to calculate that embedding vector on our search term by invoking the adder language model. And then once we've got those articles, we concat them together, put that into the system prompt, and then feed that to GPT. And it's come up back with a very apt description. So it says it takes a substring from the beginning of a string up to a specified delimiter, which is exactly what it does. It helpfully gives us the syntax. You can see we're not doing markdown formatting here. It provides some descriptive information around each of the parameters there. And then also, because we started with a semantic search here, we can actually return the list of articles that were referenced. So I can see those articles and then provide a jumping off point so that others can, like if that didn't help you enough, you could still drill into those articles to get more context on it. I'll give you another example of how like subtly good this can be. So one of the features in our platform is that you can design a workflow and then publish it as an API. So, and there are a few reasons why you might get a not found response back when you try and invoke that API. So I could say getting a not found when invoking an API-bound workflow. So we obviously have a few help articles that relate to APIs, and particularly there's one that deals with some troubleshooting steps, and it's actually going to be able to draw on that article and be quite articulate around expressing what the issue might be there. So here it's giving me a list in its usual sort of form. So does the template that you're invoking match? Check that you've published the workflow, check whether it's in a particular environment. We have a test or a prod environment, for example. So all incredibly helpful suggestions. And then over here, I can see that it referenced, for example, our troubleshooting API binding help article. So it's been able to reform, to consume that text and then present that back in a way that's context specific. So those are the use cases that we've been able to apply it for so far. I think some general takeaways, we're definitely not done. It's still quite experimental, but we have a lot of confidence this is going to make it to prime time. It's looking very promising. I think a key thing is don't use AI when you can build rules engines. If you can do rules engines, you don't need AI. So use it where like more intelligence is needed to respond to something. Determinism, very important. So ratchet that temperature all the way down to 0. I think that's important for business use cases. Speed trumps accuracy in most cases, just so that you can iterate your kind of your cadence that you're able to operate at. And then, as I showed you earlier, if you use a simplified response, don't try and emit a JSON, for example. Emit text that you can parse, because then you can handle partial response degradation. So that's it. I think, yeah, please go ahead and do a rate of this talk. And we do have a promotion running at the moment where you can certify onto our platform. We'll give you free access to our Udemy certification for that, and then we'll also give you a Take-A-Lot voucher when you complete that certification. We are looking for engineers, so if this is the sort of thing that appeals to you, I'd love to hear from you guys. And finally, we did have T-shirts at the stand. We're mostly out of them. There are some left, but we are taking a wait list as well. So if you want to leave some information, we'd be happy to send you one in the next few weeks. Thank you. If there's any questions, we do have a few minutes still. Yeah.
Yes, my name is Richard.
Hi.
My question is, firstly, I've got two. The first one is, can you connect multiple quick maps? The second one is, how do you ensure repeatability, as you mentioned, for unit testing and so forth?
Yeah, I mean, you can cascade quick maps on top of each other. I mean, that's not really an AI sort of functionality. But in terms of ensuring success, I think you don't always know exactly what's going to come back. What's deterministic is the system prompt that you've constructed, but you don't know for a specific use case whether you're going to get a reliable, successful output. So one thing that ChatGPT can't do is say nothing. It's like impossible for it to say nothing. It's literally a limit of how it's built. So it's useful to say, if you don't know the answer, say error or something. And then you can literally match on the word error and give the useful an error message. But being able to gracefully degrade the response. So if you're asking it to do something and it gives you something back, can you break down that response into useful individual bits, even if not all of it succeeded? I hope that's helpful. There we go.
Cool. Thanks, man. It was quite impressive. A question on the prompt and the response that you get coming out of your version of that, right? Does that go back into the LLM?
Yeah, so the system prompt and the user prompt get fed in on every iteration. And by the way, there's a lot of talk about prompt engineering. It's like, mostly like if it doesn't want to do something, it doesn't matter how you change the words up, it's not going to do it. You actually need to fundamentally change your approach. So there have been some cases where we've sort of nudged it in the right direction, but sometimes it's just best to think your overall architecture or try moving something from the system prompt to the user prompt or vice versa. But I think too much is made of like the exact magic incantation that will solve this every time. There's just no such thing.
So I'm more concerned from a sensitivity perspective. So the data that you actually push out or pull in goes back into the model, and that's then available for anyone else to question.
So OpenAI have a policy. They changed their terms of service several months back around, I think they say they keep it for logs, but they give assurance that they don't use it for training. And I think what we're going to see, there's a lot of open source stuff going on. The open source is nowhere near at the level of 3.5, but currently open source would be the only way you could run the model entirely on-prem. I think large organizations are going to have access to being able to build the entire thing on-prem. But ultimately, if you're using a cloud offering anyway, you're using an S3 bucket, you're using a SQL database, it's fundamentally no difference. If you can trust the vendor, you're putting the same data into their cloud already. But having said that, it's generally these use cases, you don't really have PII sitting there. So it wasn't too much of a concern for us. But yes, you are round-tripping that data. At least you're sending it into the LLM. Yeah.
You mentioned fine-tuning and that it can actually break the underlying model. Did you guys actually attempt that, or did the research phase already show that?
Just reading. Literally got vector search working on the weekend, so we're kind of under the gun there. But I think training is very hard to get right. It's very specific the way that you should break the tokens down. There's not that much literature about it. So often you'll find these Python libraries that they're built a certain way. Like there's one will break words down into 4 characters at a time and feed that in, but there's no explanation of why. And then another one won't. And I think you're liable to do more damage than good. I think prompt injection, if to answer the question you only need a small amount of information and the hard part is finding the right bits of information, then I think a search and a prompt inject is probably a more appropriate way to do that.
Hi, I have a two-parter. The first one is, did you use any specific libraries like LangChain, or did you use the Azure library type things?
So it's Azure APIs. And then on the client side, it was interesting to me, even MSDN documentation makes use of Python, which is not a language I'm very familiar with, but that's where all the machine learning is happening. So the only thing that we've had to implement client side is that cosine similarity, which is actually a fairly simple function. Other than that, everything else is done within Azure by targeting those models.
My second question was exactly about the vector and the embeddings. Are you doing basically a scan of your entire database on each query, or are you making use of any of the...
Yeah, so at scale it would be inefficient because you do have to produce a score ranked against a search term for every document in your corpus. But most of the time, even if you had 1,000 help articles, it's not that much. And so if a user has to wait 1 second to get the results back, you can do that on commodity hardware. It's not overly expensive. It has to run a math power operation, 2 of them for each dimension in the vector, so it's like 3,000 of them per article. And it'll chug through that comfortably in a second, even on a single core. So not too bad.
Do you have a sense of where the tipping point would be where the corpus becomes too large?
Really couldn't say. I mean, it's probably down to user experience, right? So whatever hardware you're deployed onto, what's an unacceptably slow time to respond? I would argue that, you saw that to generate one map arbitrarily took 30 seconds when the time before took 3 seconds, and there's not really much difference in the data. So these things are not rolled out properly. I think these companies are scrambling to scale their infrastructure. So I don't know what normal is going to look like, but these are kind of heady early days, and I think things will get better and more performant. And so by the same token, if you can give someone a contextual response, they're probably okay to wait longer than that, to wait longer for that than just a regular search match, term match.